Alright, ladies and gentlemen, welcome back to Calculus 1. This is the second lecture in the YouTube series. We just got done talking about average rate of changes, which is the slope of the secant line, and how we use that to approximate the slope of the tangent line. But the concept that you're supposed to get out of that video, because it's a very, very tricky thing to kind of get out, was this idea. And just to recap really quickly. Oops, what did I do? I broke something. What did I do? Ah, there we go. And then we'll do one of these, and we're ready. Alright, so the slope of the tangent line, I remember, and we were trying to approximate, if you remember the previous video, what the slope was at this one point. And what we do is, because we're looking for that, we're looking for the instantaneous rate of change, which is the slope of the tangent line. So here's the tangent line, right here. What do you think? If I can draw this correctly. I'm going to draw it as accurate as possible, because without accuracy we have nothing in society. I believe this to be true. And this is a gigantic concept, because without this we wouldn't be able to do a lot of the things we do with vehicles, as far as testing, as far as being able to predict what's going to happen at any particular instant. One particular example of this is the stock market. We're always trying to figure out how it's changing. Rather than what the value is, we need to know whether or not it's going up or going down, the change. Because if it's going up, we don't do anything. We just wait until the money makes. It's when the change happens and we predict it's going to go down. That's when we need to sell, right? And that's when you get the concept of doing something at that moment, right? The output. But it's not done because of what's happening at the output. It's done because of how it's changing. And that's the big difference. So we were trying to approximate the instantaneous rate of change. So we started off by saying, hey, let me look at this point that's right here. And maybe we could use the average rate of change to approximate the instantaneous rate of change. So we did one of these. And we took it, we said, okay, there it is. But if you looked at your eyes, you're like, okay, this is terrible because of this one reason. We use this point. We're trying to see what's happening at this input, which is 3. So we chose this point. It was garbage. So what we did instead is said, okay, choose a point that's closer. So we creeped in. We said, okay, instead of here, let's go in even closer. Let's approach it even closer. Let's get closer to it. If we do that, then the output get closer here, right? Which means that now our line looks like this. If I can get this thing to work right. Looks a bit like that. Now, does that look like our other line? Absolutely not. Okay, it's still not a good approximation. So we said, let's get even closer. So instead, we said by getting closer, we would do this. We would creep a little closer, and this value would creep so stinking close that it'd be right here. So notice our 2 points are staying near, smack on top of each other, which gave us an excellent approximation of what that tangent line was. Okay, even though this is what the picture is telling, this is not the idea we're ready for yet. We're going to get there, because when we find instantaneous rate of change, I'll just drop the bomb on you. It has a big name, and it requires a concept before it. Okay, the big name that it's called, the instantaneous rate of change is called, is the derivative, which is the slope at any one point. Okay, that's the derivative. Okay, the rate of change at any one point, the instantaneous rate of change at any one point. What's the 1 point? 3, 2.9, 2, 0. But how do we get there? We have to approach it and see what happens as the intervals on the average rate of change gets closer. So what does this mean? This idea of approaching brings us to today's lecture. Today's lecture, we'll be talking about limits. Just in general, of a function. Can't spell today, guys. Of a function and calculating them, right? So I feel like finding a limit of a function is easy if you have a picture. And we'll start with a pictorial view, but then we'll start looking at it from an algebraic aspect. If we just took the algebra of this, then we would be able to really talk about what's happening without drawing a picture. Then we really know how functions really working, or how it's really operating. Okay, but I do want to draw you to this word, limits. I want you to think about real life. What does people tell you? Okay, well, how have you used the word limits? How someone told you? If someone told you, I've reached my limit, or I'm approaching my limit with you, or they tell you something good, like, I don't know, Oh, perfect example. I've reached my spending limit, right? We often think about that as a set value, right? Like it's at a certain point and you reach it. But what happens is you spend. So if you're spending, your spending limit is $3,000. How do you reach it? Well, you gotta approach that guy by spending in increments until you end up getting to a point where you know where it's gonna lead to, which is $3,000, which brings us to our first giant point. Okay, when we start talking about moving or creeping closer towards a certain value, because most of the time we don't know what the limit is, we're trying to figure out what that is. Okay, so if I ask you, what is your bench press limit? If we're talking about bodybuilding, okay, let's be real. A guy who benches 315, I guarantee you he doesn't bench 315. He benches more. Possibly. I can almost guarantee you he can get more out of that. It's just the weights only come in certain sizes, so most he can fabricate on the bar is 315, okay? So which is 345 plates on each side. So what does that mean? Is that to figure out his actual mystery limit, you would have to get closer and closer and closer, but unfortunately, the weights don't make these increments to actually get there. Okay? So this is the general idea of how we're going to take an idea how to deal with limits, is to figure out the point. We can't even plug something in to get that output because it doesn't exist. The methodology doesn't exist. But the idea is can we find some way to approach it? Okay, so I actually want to go through and talk about a couple different examples for you. So I note everything that we're talking about here are as the x values are doing something, what is happening to the y values? Okay, and that's what we're talking about. Like as the weights approach a certain thing. How much does the power increase by? Okay, so hopefully we can get down to some deeper conceptualization of this. Okay, so here we go. So with all this being said, I'm going to tell you the big nitty-gritty. When we're talking about finding limits, just in general, and I know this is a freaky concept because it always makes me nervous when I first initially start about it because I always want to relate things to real life. We are only interested, okay, in what happens to the outputs as the inputs, which we call x in most cases, approach a certain value. So this is all circling around you going towards a certain value, like when we did with the approaching 3. We made our x values get closer and closer and closer to 3, and we looked and see what was happening to the y values. Okay, approaches a certain value. Let's call it, I don't know, a. Okay, so what does this look like? We need to talk notation because we're not going to keep writing this. This is not math. Math is all about doing things in a clean and concise manner. So let's talk about notation. Okay, notation-wise, we use this. To symbolize this, we say x approaches a value a. So let me draw you a number line. This is your picture view. If your value a is right here, your x values are approaching, which means they're not set values. It's kind of like running, right? If you see somebody running and you take a picture, the picture is standing still. It's standing still. What you want to do is take multiple pictures, and that's what's happening. If this is your x value, it is constantly getting closer and closer and closer to a from the left side, and it's getting closer and closer and closer and closer to b to a from the right side. Okay, so this is what we talk about when we say x is approaching a, is that it's approaching from the left and it's approaching from the right. Now, sometimes we're interested in just what happens on just one side alone, what just happens on this side, right, where it says, oh, what if x is just approaching from the left? Well, these numbers over here are less than a. So we actually have notation for this as well, and I think it's important we understand the language, because if we don't understand the language, guys, sorry to say this, but it's not going to work out well. My computer is having a mental breakdown right now. Alright, so let's understand the language. From the left side, this means x approaches a, and all the values here are less than a, because it's a number line, right? Things on the left are less than. So this is from the negative side, the less than side. Everything over here is x approaching a from the positive side. Okay, and it seems good because when these two values actually tell us the same story, then we know that our limit's actually going to be something good and actually exist, which is nice. Okay, so let me check the time. Boom. All right. So now that we actually have an understanding about instantaneous, limits and just some of the notation and what we're trying to do, let's go back to our baby giraffe example or baby hippopotamus example. Okay, and I'm going to bring my picture. Actually, I kind of want to post a new picture down here. So let's do this. Control V. Okay. So let's say I'm going to use the exact same function, but this time I'm trying to figure out what happens to the inputs as it approaches a particular output. So in this case, it's going to be what happens at t. Okay. So actually, let me give you a different graph. I want to give you different examples. Different examples are very important. So let's say I wanted to do this. Boom, 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 boom. Okay? I wanted to do this. I say, what happens to the outputs, right? And how do we write outputs again? F of x. Oh my God, I can't type today. Can't spell, can't type. What am I going to do? As the input x approaches, which would be that little arrow, 2. All right. So I'm always going to tell you guys that common sense matters more than anything. Okay, so this is our question. Okay, so this is our question. If I can get it to put a question here. Okay. But I want to give you guys a different function. That was the whole point of all this, is to give you a different function. Okay, so for what's the function? Well, here's the function. I want f of x to be equal to 3x squared minus 1. So what's the idea? This is the idea, guys, and this is what I need my decimals calculator for. So I'll put my function in here. 3x squared plus 1 minus 1 minus 1. All right. So hold on one second. So first things first. First things first. If we end up taking a look at this, then what ends up happening is, all right, guys. So I'm sorry, I had a little distraction in the other room. I had to pause the video. All right, guys, let's get back to it. So now that we're looking at this particular line, let's take this, and what I want to do is we want to see what happens to the inputs as it approaches that specific output. So let's do this. I want to hopefully pick this up if it'll let me. Boom, move it over, not there, maybe here. Let's blow it up a bit. All right, so I want you to think about this. Now, here's something I want to keep in mind about the limit, okay? Do not, in any shape, form, or fashion, think it is about the inputs. Remember, it's about what's happening as the inputs are approaching. So I'm going to show you what your mentality needs to be. So we're trying to predict what's happening at 2. That's what we're trying to predict. We're not plugging in anything at 2. We're trying to see what the outputs will be at 2. Now, this is a very pretty graph. In real life, things don't look like this. All right? So I'm plugging in x value. So I want to get closer and closer to 2 like I did in the previous example. So 2.5, 2.1, 2.01, 2. See how close I'm getting? I'm getting so close that it'll be so clear on what it has to be. Actually, let me not even put in 2.5. I feel like that's too far away. All right, and then I'm going to approach it from the other side too. How about this? 1.9, 1.99, 1.999. Okay, so I've already done the values, which is nice. I plugged them into my function. It gives me 12.23. This gives me 11.12. This gives me 11.01. Okay, so automatically, if you look at the values, they're getting smaller. The y values are getting smaller. To what value? I wonder. I have no idea. Likewise, if we plug in 1.9, it'll be 9.83. It'll be 10.88. I did all the calculations before the video, guys. This is 10.99. So it kind of gives me this idea that they're both approaching some goodness. So I'm going to show you how we're going to write this. Now, we are automatically what I would probably draw the conclusion of. Note, I am not plugging in 2. That is not what I'm doing. Okay, I just want to make that very, very clear. What I'm doing is this. I'm saying, and everybody watch the idea. I want to say that as x approaches 2, and you can kind of see it, as the x's approach 2, the outputs, so as the x values are going to 2, what's happening is the y values seem to be getting closer and closer and closer to a number. And they're flying up, getting closer to a number. What is the number it's getting closer to? Don't know. I didn't even make a copy of it. So let me go ahead and do this. I'm going to get rid of this nonsense. The idea is that as x approaches, and then I'm going to write some good stuff, as, and this is the way you need to think about it. So as x approaches 2, which side are we coming from? The positive side or the negative side? The positive side. Then f of x approaches or gets closer to what looks like to be 11 from the right side. And as x approaches 2 from the left side, the function, yet again, the y values seem to be getting closer to 11. So what's the conclusion we can draw? So if they're both coming from both sides, we can say altogether then as x approaches 2, doesn't matter where you're approaching from, just as it gets closer to 2, doesn't matter where, left or right, that the function has to be getting closer to 11. That's it. That's it. Note, again, note. F of 2 does equal 2, guys. F of 2 does equal 11, okay? But that's not what I did, okay? And this is why. Because f of 2 at that point, 99.9% of the time will not be the output. Because think about all the different functions you know. And then I want you to think about if you were to take pieces of those, piecewise functions, or those ugly functions that have asymptotes and holes in them. Most of the time, that's what we're trying to figure out. We're taking limits to is where are those things going. We don't care about a continuous function. That's what this is called. When it's continuous, you could draw a pencil without picking it up. Okay, so try not to actually plug in the value because that's not what we're doing. Okay, so let's write this now like mathematicians. Okay, because mathematicians will write like this. To write this, we write the actual word limit. And what we're trying to do is figure out the limit as x approaches 2 from the right. The function should approach 11. That's what that means. So this verbiage, this languaging, this symbology is what we use. And likewise, if I took the limit as the inputs approach 2 from the left-hand side of the function, it equals 11. And thus, the conclusion we want to draw, just written in math notation now based off these two premises, is this, that the limit as x approaches 2, does not matter from which way, of the function equals 11. This is the conclusion you want to draw. Now, let me be very, very clear and concise with you guys. If you skip a word, right, or you try to make up your own languaging because you want to be lazy and say x approaches 2 and x approaches -2 all at the same time, I tell this to my class because I want to be very, very clear. You make up your own language, I will make up my own grade for you. Okay. This is like, they would be the equivalent, okay, and I don't know how passionate you guys are about culture, but math is its own language, its own identity, its own culture, same way engineering is, same way the country of Korea or China or Vietnam or any Middle Eastern country that speaks a different language. It'll be the equivalent of you going to that country and telling them they're speaking their own language wrong, okay? Understand how the language is being spoken and what the language means, okay? So, moral of the story, plugging in 2 was a coincidence. It's a coincidence that it's 11. It is not always the case. So let me give you a clear and concise example of what I mean. Here we go. And then this is where I think will be a good time to cut off the video. Okay, here's an example. I need black. Black is a great color to put examples down for. All right, I want you to say, let's let the function be equal to this. I want it to be x plus 2, which is degree 1, or linear, if you remember how to graph piecewise functions, which you absolutely need to know how to do. Okay. For if x is equal to 0, and then x squared plus 2 if x is less than 0. All right. So I hope, and here's your job. Find the limit as x approaches 0 of f of x. Yeah, guys, here we go. This is the nitty-gritty. So first things first, let's draw a picture so it's clear. And I'm going to do my best to try to show you all the elements, but we are running low on time, so I want to, because I'm trying to adhere to keeping every video close to 20 minutes. And I'm sorry about the rambling in the beginning of the video, but I wanted to make sure that the basics was there. All right, so I want to ask you guys a question. Where is all the action happening in this piecewise function? Notice these are what they do. This is not where the action happens. The action happens with the domain. Everything seems to be happening around 0. Don't you get it? If it's bigger than 0, do this. If it's equal to 0, do this. If it's less than 0, do this. So if it's bigger than 0, it says go to x plus 2. Do x plus 2. So if it's 1, right, you get 3. Boop, boop, boop. If it's 2, you get 2. If it's 2, what do you get? 4? Okay, so look, but hold on. Can I plug in 0 here? No, I can't. And this is a big point. And a lot of people, especially had me for 1050, I tried my hardest to say, oh, just say, oh, plug in 2, plug in 1, plug in 0. You plug in 2, you got out 4, you got 3. When you plug in 0, nothing should come out, even though a lot of people say plug in 0 to get 2, and this is going to be an open circle. You don't know this, but what they were really giving you was a shortcut for the limit. Yeah. So this is going to be an open circle. So you needed something to look like this. Okay, now when you plug in 4, which I said I'll denote this with blue. Let me slow down and choose my colors correctly. My output should be 4. Okay. If I do the other one, which is quadratic, same kind of idea. It looks something like it's degree 3, but it should be something like this. Should be there and there. So this is our piecewise function. So here we go. Time to break it down. In order to figure this out, right, and this is what they want us to find, we know that we need to find exactly 2 things. We need to figure out what happens. Remember, this all surrounds this x value. So I need to figure out what is going on here. As x approaches 0 from the left side, what does the function do? And as the inputs approach 0 from the right side, what does the y value do again? Function of the y value is what I like to look at it. So let's look at the right side. We can do this from a pictorial kind of sense. Okay, so as x approaches 0 from the left side, okay, so it's approaching 0. The x values are approaching 0. The y values seem to be coming lower. So if it was right here, that's a y value. If it was right there, that's another y value, right? And it gets closer and closer, but it seems like it's going to go to what value? Looks like 1. Okay, so we'll make that a giant 1 and say yay. Okay, looks like it's going to 1. But as x approaches 0 from the right-hand side, the y values seem to be getting closer and closer to 1 yet again. This will tell us that this is the limit, and once again, let's use good notation. The limit, the way you would actually write this. This is your brain. This is how you should be thinking about it. The way you should write this on your paper is this breaks down into 2 pieces that need to match. If they don't match, then it's no good. The limit as x approaches 0 from the left-hand side of the function should approach 1. And the limit as x approaches 0 from the left-hand side of the function, that approaches the same value. So we could draw the conclusion finally that the limit as x approaches 0 of f of x equals 1. Check. Okay, and this is kind of the idea. Now note, this is the gigantic note piece of the puzzle. If f of x, if we were to plug in 0, because everyone says, why can't I just plug in 0 and figure out what it is? Because you plug in 0 in this piecewise function, this ugly function, 0 gives you 4. Note, they are not equal. They don't have to be equal. So more of the story, do not plug in the input. What you have to do is take the limit from the left and the limit of the right and try to get a good idea or central tendency of where it's going to go. Okay, so this is the general idea of limits, and this is how you'd approach it from a pictorial view. Okay, it's really that simple. Now, so the moral of the story is that the limit from the left-hand side, so in order for the limit as x approaches a value a of f of x should be, let's say, this thing. In order for this thing to happen, this is just a number L. So in this case, our number L was 1. Okay, we'll call it the limit point. Then two things have to happen. Condition 1, and these both have to happen. That the limit as x approaches a from that left-hand side should go to that value L, and the limit as x approaches a from the right-hand side should go to that value L. And if both of those match, then good. If they don't match, then we say that the limit does. So if the two values are different, we say the limit does not exist. And as a matter of fact, I'll do this for you, since I think we're already way over. Oh my God, this is going to be a 30-minute video. I'm going to make a slight change to this graph. Watch this. If I change this 2 to a, let me change it to a different color, 3. Then that means this red graph no longer should be here. It should be here. Oh, by the way, I missed a hatch mark. This should be 1, 2, 3. Good. Okay. Now check this out. This means that as x approaches 0 from the left-hand side, it's still going to go to 2. Oh, crap, 2. All my values are wrong. All my values are wrong. This should be a 2. That should be a 2. That should be a 2. That should be a 2. I drew the graph wrong. The conclusion should be 2. Unfortunately, they still don't match. Sorry, guys. Major mess up there. So now let's take a look at it. As x approaches 0 from the left, it's going to approach whatever value that was. Remember, I thought it was 1, but I messed the hatch marks up. As it approaches 0, it should be 2, right? So that still hasn't changed. That's still 2, okay? But check this out. From the right-hand side, it approaches 3. So now the question is this one is 2, this one's 3. So the limit does not exist. And guess what? The output's still 4. But do we care about the output? No, we do not care about the output. So you'll just write DNE, which does not exist. It's really all that simple just from looking at a picture. All right, guys. Sorry about all the hang-ups. Sorry about the hatch mark. And sorry about the beginning. Hopefully, we'll be able to get this solid as it goes on and on and on. Again, this is Rush Mahaber. In order to do something you've never done, you're going to have to go someplace you never did. I'll see you in the next video. Bye.